Hello, my name is Enes Ceran. I am a computer science student at Bilkent University. In this video, I will be presenting to you my Physics 102 project, which is the inspecting the behavior of an RLC circuit driven by an AC source. My main purpose is to see how a simple series RLC circuit behaves when I change the frequency of an AC signal. I want to observe how resonance and impedance changes, and at which frequency the circuit lets the current pass most easily, and how the impedance changes around at that point. At the same time, I also want to understand the role of the resistor. First, I use one series resistor, then I add the extra resistor and repeat the measurements. By comparing these two cases, I can see how increasing the resistance reduces the resonance peak and how it makes the circuit less selective to a band of frequencies.
For this experiment, we need an inductor, capacitor, resistors, breadboard, wires, function generator for generating AC source, and of oscilloscope for visualizing the voltage.
After building the series RLC circuit and connecting the signal generator and the oscilloscope, I started by choosing a set of frequencies around the expected resonance. I kept the output voltage of the signal generator 5 volts. For each frequency, I measured the voltage across the resistor using the oscilloscope. From this voltage, I found the current using Ohm's law, and using the current and total voltage, I can calculate the magnitude of the impedance at that frequency. After that, I added an extra resistor in series with the same circuits, without changing anything else in the setup, and measured the voltage at the same frequencies to observe how increased resistance changed the resonance. When I plotted the impedance and current as a function of frequency for the first case, I saw that values fit the theory and formulas. The impedance was relatively high at low and high frequencies, and it reached a minimum in the middle region, close to the resonance frequency, predicted by the values of L and C. The current curve showed the opposite behavior. It had a clear peak in that region and was smaller at low and high frequencies. In the second case, with the extra resistor, the resonance frequency stayed almost at the same place, but the minimum impedance became higher and the current peak became lower and wider. This shows that increasing the resistance doesn't move the resonance, but it reduces and smooths out the resonance peak, which is exactly the damping effect we want to observe. But I had a small deviation from the theoretical results. The resistor, inductor and capacitor don't have exactly their labeled values, so the resonance frequency is slightly different from the ideal one, with a 3% error rate. The inductor and cables also add some extra resistance. Also, I measured the frequency in steps instead of continuously, so I might have skipped the exact points of maximum current. All of these effects can cause small differences between theoretical and measured curves.